GP Calculus on the topic of arc length continued. So on this problem, it gives you a table that has the x coordinates here, f of x, and the first derivative of f prime of x here. And you can see it tells you selected values for a differentiable function. And remember, it's differentiable. That also means it's continuous. And the important thing as it relates to arc length is, remember, the arc length formula only works for smooth curves, or curves that are smooth on a certain interval, where there's no corners or cusps. So the differentiable also tells you we've got a smooth curve that we can use the arc length formula on. And then here it asks us, it kind of combines two different concepts together. It says using a right Riemann sum. Remember, we use these to approximate integrals here because we don't have the equation. We just have, for f of x, we just have the table of data. And it says three subintervals of equal length. What is the approximation of the length of the graph of f for the interval 3 to 9? All right, so let's first write down, using the arc length formula, since we know it's differentiable, a smooth curve, the integral from 3 to 9, and then we'd have the square root of 1 plus f prime of x squared, is that formula, times dx. So this is the integral we're trying to approximate, and we need to approximate because we don't have the original function f of x or its derivative f prime of x here. And we have three subintervals of equal length, so remember we can use that to find the width, and this only works this formula for equal subintervals, which we have equal subintervals. So remember, you take the width of the whole interval, in this case b minus 8, 9 minus 3 gives you the width of the whole interval, and then divided by the number of subintervals we have is 3. So that gives you 9 minus 3 is 6, divided by 3 gives you 2. So now we know the width is 2, and now we can draw our number line based on that. Starting from 3, going to 9 by 2's. So add 2, 5, add 2, 7, add 2, 9. So there's our three equal subintervals we're using. And remember, all the Riemann sums are rectangles. In this case, we're using the right endpoint to get the height of each one. So to make it a little more convenient to write down, though, initially, I'm going to call this whole function here that's inside of our integral, because that's usually we just integrate like f of x, or just one function, but here we're approximating this integral, which is a little more complicated. So this, since it represents the length of the graph, or arc length, same thing, I'm just going to call it L of x for short, this whole thing, so that we can write this down a little more compactly, at least to start with. So we take the width 2 times the height, the right endpoint of the first subinterval, you can see from 3 to 5, it would be 5, so L of 5. Plus, the width again is 2, arc length of the second one using the right endpoint would be L of 7, plus 2 times L of 9. And now we can substitute those in for x, it's 5, 7, and 9, and into L of x, which is the arc length formula we have. This is called the integrand, what we're integrating here. And what else you can do also, to make it a little simpler, notice since they have equal widths, you can actually factor out the 2 out in front. And then when you substitute in 5, you'll have the square root, 1 plus f prime of 5 squared, and then plus the square root of 1 plus f prime of 7 squared, plus the square root of 1 plus f prime of 9 squared. can get these values from the table. So f prime of 5, we can see right here, it's not f, it's f prime, is 3. So 3 squared is 9 plus 1 gives you 10, so that would be the square root of 10. F prime of 7 is negative 1. Negative 1 squared is 1 plus 1 gives you 2, so square root of 2. Plus f prime of 9 is 0, so that's just 0 plus 1 square root of 1 is 1. So you could leave it like that, or you could distribute out the 2 to get 2 root 10 plus 2 times the square root of 2 plus 2. And they don't give you specific units here, so remember arc length is just one-dimensional. So if you want, you could just put units. We don't know if it's centimeters, inches, meters, we don't know what it is. So you don't have to put the units, so you put it. So that's how you kind of combine our Riemann sum approximations with the arc length formula. Notice we didn't use f of x at all, because a common mistake on this one would be to integrate, try to use f of 5, f of 7, and f of 9 without, and just basically ignoring the arc length formula altogether. That would approximate the area under the curve of f of x, but that's not what we're asked to approximate. We're asked to approximate the length of the graph. All right, let's take a look at the next one. This one, it says the graph of the function g on the interval -7, 7 consists of a semicircle, we can see right here, a quarter circle right here, and 3 line segments. 1, 2, 3. And what is the value of the integral from 0 to 4, square root of 1 plus g prime x squared dx? Give a reason for your answer. Okay. So the first thing you want to recognize is, oh, this looks like our arc length formula, right? It's got 1 plus inside the square root, g prime squared, and notice it's from -4 to 0, and it is. So there's a couple different ways you could go about figuring out the value of it. You could try to figure out g of x. It's not that bad. G, from -4 to 0, it's the semicircle. You could just derive the formula for this semicircle looking at the center and the radius, and then find the derivative of that, plug it in here, and then integrate that from -4 to 0. You could do that, or you could realize, well, wait, what does this really represent? This whole integral really just represents the arc length from -4 to 0, but we can see since it's a semicircle, we can just use our circumference to figure that out, right? So notice it's half the circumference, so it'd be 1/2 times the circumference formula is 2 pi r. But in this case, r, you can see the center would be right here, so the radius would be 2. That would be 4 pi, would be the whole circle circumference times a half, so it would be 2 pi. So that's a lot faster and more efficient than actually using the integral here. And then it just says give a reason for your answer. So we can say what it represents. Help us give a reason for your answer. Integral from 0 to -4 to 0, the square root of 1 plus g prime x squared dx is the length of our graph G from, you don't have to word exactly like this, just as long as it has the same components to it, from x equals -4 to x equals 0, which is a semicircle with a length of 2 pi. And then something similar for part B. What's the value of the integral from 4 to 7, of the same integral here. So from 4 to 7, you can see that's from here to here. There's our quarter circle. And we can calculate that one. We'll go 1/4 of the circumference, which is 2 pi. Here, the radius, the center would be here. You can see the radius would be 3. So that would be 6 pi, would be the whole circle times 1/4. Would be 6 pi over 4, which reduces to 3 pi over 2. prime of x squared. The x is the length of G from x equals 4 to x equals 7. Which is a quarter circle. With a length of 3 pi over 2. Let's take a look at one more without calculator, then we'll look at one with the graphing calculator. So this one says write but do not evaluate. So we're just setting up the integral expression that gives the length of the graph. Sometimes they call it arc length, sometimes length, it's the same thing. Y equals cosine squared of x from x equals a to x equals b. And the importance of this expression here is this is telling you which one's bigger. In this case, b is greater than a, or a is less than b. And they're both greater than 0, which is important because if we didn't know that, these might, notice it's with a square root, they might give you imaginary answers. So here we do need to know that in order to know that we can actually have a link, the curve actually exists there. So we set up our integral here. In this case, since we know a is the smaller of the two, the integral from a to b, and then the square root of 1 plus, but then we need the derivative. So let's go ahead and find that here off to the side. If we rewrite this first, y is equal to cosine, and then instead square root of x, the same as x to the 1/2. And then when we find the derivative, dy dx, start on the outside and then use the chain rule. The derivative of cosine is negative sine. X to the 1/2 stays inside as it is. And then times the derivative inside using the power rule would be 1/2 x to the negative 1/2. So then if we simplify that, let's see on the numerator we have negative sine, and we can just rewrite this as square root of x back in radical form. And then the 2 is on the denominator already. And then if we move this denominator with a negative exponent and switch to radical form, it would be 2 over root x. So that's our simplified derivative, so that's what's going to go inside here and get squared. So it'd be negative sine square root of x over 2 root x squared. And then times dx. So that would be the integral to set up. And obviously, since we don't know the exact values of a and b, wouldn't be on the value of it exactly. Even with your calculator, that's as much as we do it. It's just set up the integral. All right, let's take a look at one more. This one we'll use our graphing calculator on. So sometimes they might apply arc length to an applied problem like this one here. So here it says we've got a skateboard track that consists of a straight ramp. Okay, so here's the straight ramp here, followed by a curved section. Here's our curved section right here, and then a horizontal ledge right there. The track is modeled by 2 linear equations. So here's our linear equations. And the function f, which is given by f of x, 1/9 x minus 5 plus 1 squared. So, and notice that applies from 2 to 8. So from 2 right here to 8, this gives us the equation of that curved section. And it says x and y. In this case, it's an applied problem. They're both measured in meters. Okay. And it says, what is the length of the skateboard track on intervals 0 to 11? So from here all the way to here. So let's start with the easy sections here, the linear ones. So for this horizontal line, you can see it goes from 8 right here to 11. Subtract those, so the length of that horizontal ledge there is 3. And then to get the length of this section right here, you can see you could draw a right triangle right here, and notice that's the hypotenuse of it. There's different ways of doing it. This is one way. You can see this is 2 from 0 to 2. This is also 2. So one way you could do it is the Pythagorean theorem. You could say, if we called this, I don't know, h for hypotenuse, you could say 2 squared plus 2 squared equals h squared, which gives you 4 plus 4 equals h squared. So h squared would equal 8. And then take the square root of both sides. So h would equal, normally you need plus or minus there, but we know this length can't be negative, so it'd just be square root of 8. And you could simplify that, pull out the 2 to be 2 root 2. So now we know hypotenuse is 2 root 2. That's one way. Or you might recognize this is actually a 45, 45, 90 triangle, an isosceles right triangle. So these are normally 1, 1, root 2. So since it's 2, 2, you could multiply the 2 by root 2 to get the hypotenuse that way. Or you can be a little faster than the Pythagorean theorem, because it's one a special right triangle. So we've got those two first. So we can say 3, doesn't matter which one goes first, plus 2 root 2. And then the curved section, that's where we're going to need the arc length formula for that. So that section, notice, goes from 2 to 8. And then it'd be the square root of 1 plus, but then we need the derivative. So let's find what that is, f prime of x. You can see you just use the chain rule here. Bring down the 2 times 1/9. I'll give you 2/9. X minus 5 now to the first. The derivative inside though is just 1. And then the plus 1, the derivative is 0. So it's 2/9 x minus 5. But then that gets squared. And then times 2. So that'd be the integral that will give us the length of the curved section. Okay. So here's where we can use our calculator to put this whole expression into our graphing calculator. So let's look at it with both calculators here. So the 84, this is the older one here, would be 3 plus 2 second square root of 2 plus, and then the integral would go math, number 9, function integrate. And then the first we need is the square root. You just got to be careful with your parentheses here. So second square root. And then we've got 1 plus. And then we need an open parentheses for the green one right here. And then we've got 2/9. So I'll put a parenthesis there, 2 divided by 9, close parentheses on the 2/9. And then another open parentheses for the x minus 5. X minus 5, close parentheses on the x minus 5. Then we need another close parentheses for the green one here so we can square it. And then we need another close parentheses on the square root. And then we can put comma, our variable's x, comma, the lower limit's 2, comma, the upper limit's 8. And put those together, we get 12.247. And here they give you the units, or meters. So write that down. 12.247 meters. So it's both x and y are meters. And you can see if that seems reasonable. Well, if we just had a horizontal line here, notice that would be 11 meters, but we can tell this is definitely further because it has this curved part here and part up here. So it should be more than 11 in this case, 12.247. All right, now let's just double check. Let's use the Inspire. And the newer 84s kind of have a similar format in terms of the integral part, what it looks like to the Inspire. So for the Inspire, we just, new document here. We can just add the calculator. We don't really need to graph this one. And we'll have 3 plus 2 square root here is control, and then that button right there, the square root of 2. And go outside the square root plus the integral is next to the 9 from 2 to 8.
And then we've got the square root again. To make it look just like it looks on paper, basically. 1 plus, this is kind of what the 84 one looks like. 1 plus, then we need, we can put the fraction, first we need the open parentheses so we can square the whole derivative. And then you can put the fraction like this with a fraction button, 2/9. And then open parentheses, x minus 5. And then make sure that whole derivative gets squared. And then dx. Oops. And I can see I've got my settings here. So it's giving me more an exact answer rather than the decimal answer. So let me change my settings. Menu, or let's see, document, settings and status, document settings. And calculation mode, notice, is on automatic. I'm going to change that to approximate. And make the default so I don't have to do that again. And now let's just highlight this. Control V, Control V, and enter. And now it gives you the decimal answer instead of this weird-looking radical answer. And that concludes the notes for AP Calculus on the topic of arc length continued.